Alright, we're dealing with chapter 21 today, which deals with nuclear chemistry. Now, nuclear chemistry, we're going to introduce it by focusing first of all on the actual main particles of radiation that we see off natural substances. Now, the naturally radioactive substances are still natural substances, but we have alpha particles, we have beta particles, and we have gamma particles. Now, we're going to see that there's an inverse of a beta particle that's actually called a positron, which will be our fourth type of radiation. And if it was on here, it would actually be a complete mirror of that blue line. It'd be almost just as sharp of an angle, but it'd be coming over here. Because it's the exact same thing as a beta particle, but a beta particle happens to have a negative charge. A positron has a positive charge to it. Alphas are the heaviest, which is why they're or the heaviest, and but they do have the largest charge. But the weight is why they don't deflect as much. And then the gamma particles are actually just gamma rays. It's actually light. It's just got a lot of intensity to it. Alright, the main particles can be grouped like so. We have alpha decay and beta decay, and there's those positron particles I was talking about. Almost all the time when I do this, I'm actually going to label that with a positive to distinguish it, because technically they get the same symbols. It's just that positron has a positive charge and the beta particle has a negative charge. Now, all three of those are actually having these guys as a product. But there's also electron capture, which actually does have an electron as a reactant. And then the last one on there is gamma radiation, and it actually doesn't affect the mass or the charge of a excited nucleus. It just, something happens in how that nucleus is put together, and the energy is released in the form of a photon, which is just an incredibly powerful light, in this case the gamma rays. Alright, our particles can be drawn out looking like so. We will also see alpha particle, for instance, with a symbol drawn more like 4, 2, and He. And sometimes the beta particle is -1e. And that really is, those simplifications are done simply because an alpha particle really is the nucleus of a helium atom, or exactly the same as the nucleus of a helium atom. And a beta decay, that is actually an electron. It's just being ejected at a very rapid rate. Then we have our positron, which is not anything that we've seen before. Positron has got the exact same mass as an electron, but it's actually a positive charge. Now, on this paper, this page, I put them on the I put those symbols on the left and right to actually specify and connect it with where we find them. So when this actually goes through alpha decay, the alpha particle and the beta particle and the positron are products. Yet now electron capture, the symbol, the electron itself, is actually a reactant. And gamma is also going to be a product. So we got 4 of these that have the nuclear radiation as a product, and 1 where it actually absorbs an electron into the nucleus and changes things based on that. Now, when we do these things, we really are just doing some simple math to figuring this out. So if I wanted to show thorium-232 going through alpha decay, I really do just actually start out by writing 232 thorium, and I do get the atomic number right off something like the periodic table. Thorium's down here, number 90. And I would show, since this is alpha decay, it makes an alpha particle. And then we just do math. 232 minus 4 is 228. 90 minus 2 is 88. And if we go back to the periodic table, we'll see that 88 is radium. Oop, I forgot my plus right there. Alright, going to do something similar for zirconium, 86. So zirconium, 86. Looking on the periodic table, zirconium has atomic number 40. We want it to go through electron capture. So we're going to have an electron on this side. And now we just do math. 86 plus 0 is still 86. 40 plus -1 is 39. Go back to the periodic table and see that that is a Y. Now, next one might trip us up, but if you notice, it wants us to figure out what nucleotide undergoes beta decay to give us cesium-133. So it's saying we want the beta particle, and over here we also want the cesium. Let's see, 133 and 55. Now we're doing math go backwards. This is still 133. 55 plus -1, 54. This was xenon. Probably the easiest thing we've done in Chem 2 all semester, because we really are just doing addition and subtraction here. Alright. Turns out quite a few of our isotopes are stable, but there's a lot more that we find in nature that are not. And actually what we're seeing here on this little graph on the left, all those little black dots are the stable nuclei only, and only the stable nuclei. Anything that's not one of these black dots that we could find is an unstable nuclei. And if you notice, this list stops up here at bismuth 83. Anything on the periodic table that has an atomic number bigger than 83 is actually unstable. There are no stable nuclei that heavy. And also, if you notice, if you really look closely, you'll see that every other row has more dots. And what we find is the odd, atoms with odd number of protons, there's fewer of those stable. So it turns out that's a factor in what helps you predict something is stable, is if it's an even number of protons and an even number of neutrons, it's much more likely to be stable. Alright, but over here on this blown up view, got more dots added. So that was this bigger section, and it really only shows the black dots on the scale over here. The blue ones on this thing are actually unstable nuclei, but they happen to give off beta. They actually go through beta decay. And we have the yellowish ones that's either going to be electron capture or positron. And we typically do group those together because we really can't tell them apart, not from what the products are. Because if it goes through electron capture or positron emitter, it actually ends up giving us the exact same products. So we kind of always just group them together. And then occasionally there's some red ones, where it's the alpha decay. Alright, when we actually expand on that, if we were to look at something that does have an even number, or an even atomic number, we find that there's a lot more stable nuclei than if it's odd. And we see that all the way along. Matter of fact, if I go back here, there's a few rows that there's nothing there. And that's, let's see, that's going to be atomic number in the 60s. Well, I know this technetium on our periodic table, 43, yeah, that would be right along in here. There are no dots at all. And that's because there are no stable nuclei of technetium found in nature. And this one must be it could be 59. Well, anyway, oh, actually, it's right here. It's 61. So this chart is telling us that promethium, element 61, has no stable nuclei. Alright, and we see that. Turns out, when you have odd numbers and odd numbers, there's only 7 nuclei on the entire periodic table that have both of those being odd, and it's still stable. For the most part, it's safe to say if you have an odd number of protons and an odd number of neutrons, you have an unstable nuclei. But if they're both even, almost all of those are stable. Alright, and we'll do a little bit more on predicting this. Alright, so we're going to base it on a few things. We're going to look at the ratio of neutrons to protons. The ratio does go higher towards neutrons as we get further down the periodic table, but once the atomic number gets to 83, none of those are really stable. So we're going to practice that on things like this. Alright, so I have neon 18. So that neon has 10 protons and 8 neutrons. Alright, I can immediately say unstable simply because it's got too few of neutrons. At minimum, you need to have 1 neutron for every 1 proton. The fact that this is less neutrons than protons, there's no way that's stable. Alright, the next one, sulfur 16, 16 protons, 16 neutrons. It's a 1-to-1. It is a small atom, smaller in size, smaller in atomic number, so it's likely it could be 1-to-1. And when we're in doubt, what we actually do to tell ourselves for sure, we flat out look at the periodic table. Average sulfur likes to be right around 32. That go along with this, we'd actually predict this to be stable. Alright, next one, thorium 236. Now the thorium actually has an atomic number of 90. So this has a lot of neutrons. But I don't actually need to look at whether or not this has enough neutrons to make it stable or not. It never is, because that is flat out larger than that 83. This is unstable simply because of that. So the number of neutrons are never going to make that better. Alright, the next one I have barium 123. Atomic number is 56. So if we did math, we could figure out roughly how many neutrons are. But heck, there's an easier way to do all this. If I want to know if something's stable or not, compare that barium to what the average barium is. The average barium has 137 protons and neutrons. This thing has a lot fewer neutrons, obviously. So this is unstable because it has too few of neutrons. Alright, so how about this? Why do you think phosphorus 31 might be stable and yet 30 is not? Well, we did say even numbers are good, so that would make you think at first that maybe phosphorus 30 is better. But when we actually look at the atomic number of phosphorus 30, we see that both these have 15 protons. Therefore, this one actually has 16 neutrons, while this one has 15 neutrons. And odd is definitely not likely to be stable. Alright. Turns out, not only when we actually see that they're unstable, we can actually predict what kind of decay they're going to go through. Typically what we find is if we have too many neutrons, we actually find the atom will go under beta decay. If it's got too few of neutrons, it'll go through positron decay or electron capture. And it's typically deviated like this. Heavy atoms go with positron, or no, heavy atoms go with electron capture. And the light ones go through positron. Now, we never actually try to predict or guess if it's heavy or light in general chemistry. We actually treat these interchangeably to a degree. Alright, and then the heavy nuclides are always going to go through, that should be an alpha. Matter of fact, that should have been a beta. But I guess I didn't get my font right. Alright, so let's see if we can predict this. So boron 12. And rather than just do it like this, we're going to write out the actual equation they're likely to go through. Alright, so boron 12. Boron has 5 for its atomic number. And if I look at the periodic table, I see that the average boron would like to have about 10 or 11. So we're going to predict this as neutron rich. So since we're predicting neutron rich, we're going to say it's going to go through beta decay. And therefore it's going to make some carbon. Alright, uranium 234. Being that it is uranium, I flat out don't even care about the number of neutrons because it has an atomic number of 92. And that 92 tells me that it's likely to go through alpha decay. And then 90 turns it back into thorium, or turns it into thorium. Alright, arsenic 81. Let's see, arsenic has atomic number of 33. And it would like to have 74 for its mass, so this is neutron heavy, just like our boron was. 81, 34. This is going to turn into Se. And then the last one, La. let's see, has an atomic number of 57. According to our periodic table, it would prefer to have 130 or 139. So we want this to be much higher. We're going to say this goes through electron capture or positron. I'm going to write out electron capture. So this stays 127, but this is going to go to 56. And it's going to turn into barium. Now, if I redid this bottom one, the 127 La, and had it go through positron, we're going to see it gives us the exact same product. Which is why we can't tell them apart at this point, because they'd give us the same product whether it goes through positron decay or electron capture. Alright, two more of these. Got iron 61 and americium 241. So 61, that's got 26 for its atomic number. Is that right? Yeah. And the average iron would like to have a mass around 56. So we're going to predict this is neutron rich. So beta decay. And atomic number for 25, manganese. How about if I do that as we normally do math? And what I mean by that, 26 minus -1, this needs to be 27. And therefore, it's turning into cobalt. Alright, and then americium 241 has an atomic number of, it's down at the bottom of my periodic table, 95. And alpha decay, simply because it's a heavy atom. 241 minus 4, 237. 95 minus 2, 91. Americium turned into neptunium. Alright. That is by far some of the easiest stuff we've done in all this. We're just figuring out neutron rich or neutron poor, or if it's a number greater than 83, and then going from there. Alright, the next thing we're looking at is what these isotopes do. Because it turns out, if you think about it, anything like uranium, being that has an atomic number larger than the 82, is going to go through decay. And alpha decay is always a possibility. But, bring up the periodic table here, since that actually lowers the atomic number by 2, uranium would decay into thorium, which is still unstable, which would decay down to radium, which is still unstable, which would decay down to radon, which is still unstable, etc., etc., etc. It's not like the uranium falls apart into something stable. It does simple alpha decays over a long period of time. Well, that's what we're showing here. Uranium-238 has this as the most favorable and the fastest decay series, where it turns from a radioactive isotope into a stable isotope. And it's going to take eons. Each one of these has a very long or short half-life, and so it takes a very mighty long time for the uranium-238 to turn into lead-206. Now, even though this stuff is dangerous and radioactive, turns out if you had any of it, it's still going to be around at the end of, well, gosh, even the end of the, or a large amount of it still be around even when the sun finally goes supernova. The lifetime that it takes to go from here to here is so long that it's still going to be around for a mighty, mighty long time. Alright, when these things fall apart and give off the particles, we can actually measure them with various different things. This is a Geiger counter, and or this is the idea of a Geiger counter. So Geiger counters were some of the earliest ones you can get. There are better ways of doing this now, but this is the old Hollywood movies when you see them holding the, it's got a long handle to a big yellow box. Gonna have a dial here, and then there's either a probe hanging out here or somebody's holding a probe in another hand, but they're holding that out and they go around there and it goes tick, 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 tick. That's the old style Geiger counter. You can still buy them. They're easy enough to get. No one really has them though. It's a weird thing to have laying around in your house is your own Geiger counter. But what that works with, there is anode wire inside a tube full of a gas, and when the particles, the radiation particles, hit that tube, it creates it knocks an electron out. They're going fast enough, they knock single electrons out. And that does this nice little effect to actually generate an electrical current. Works relatively well. They can be scaled up for higher amounts or lower amounts because there is residual radiation in places like hospitals and the like. So they actually want to measure low amounts, and you want to build them so they measure higher amounts. That's the old school way. Newer way, this is more like a solid state. All this can be done on a microchip. But these are little lenses that do about the same thing. They run a different current through there. When the particle goes in there, it kind of cascades down through here. But as it hits these little plates, how they've done the plates in there, it amplifies the voltage. So a single particle creates a larger amount of electrons as it goes down. Like I said, these can be done on chips now, so you can actually go to places like Amazon and you can buy Geiger counters. They even sell them that look like little headphone jacks for like your phones. Kind of have those little prongs in them. And apparently they work reasonably well on certain types of radiation. They're good for gammas. You can get them good for X-rays, which aren't quite the same type of thing here. That's dangerous, obviously, but that's not radiation per se. And I think you can get to beta particles, but the bigger ones you need something different. But they're it's odd. In a connected world, you can have that, plug it in your phone, and then share that data with anybody on the internet on how bad the radiation actually is in your neck of the woods. All right, when they decay, the number of decays is related to how unstable the nucleus is. And we have a lot of different units here. So the actual standard unit, the BQ, just talks about the number of decays in a second, or 1 decay per second. So if it's 1,000 BQs, that does mean there's 1,000 decays per second. The Curie is a huge number of decays per second, 3.7 times 10 to the 10th decays per second. And that number came from, that's how much of radiation came off, or that's how many particles came off of radium-226 if you had a whole gram of it. Apparently back when they studied it, to get that 1 gram of radium-226, they had to like purify a sample of ore, and it's something like a ton's worth of rock gave them that 1 gram. So a lot of safe material to get that 1 gram. But once they had it, they had this 3.7 times 10 to the 10th decays per second. So this thing was flying apart very rapidly. We're going to see, I got something really messed up here. This decay rate is the first order. And if we back up to like what we saw in kinetics earlier in the semester, you might remember this equation, hot and T. Well, that's kind of the same thing that happens here. We actually can study the concentrations of our nuclear isotopes, or we can throw in decay rates in there because they are proportional. The decay rate is comparable to the amount that's in there. And the K is actually kind of like how long or short the half-life is. The larger the value is, the shorter the half-life is. But most of the time we end up using half-life. But since all these are first-order equations, we do know this nice thing. The half-life is the natural log of 2 over K, or if I wanted to plug it into this thing, natural log of A at any time equals the negative of the natural log of 2 over the half-life times the time plus the natural log of A hot. That'll work all the time now because that's actually the equation we're going to use. All right, so half-life is much more versatile in nuclear chemistry, because since they are all first-order decays, the half-life means the same thing, and they actually can be measured in various different times. So what we have here is a bunch of beryllium isotopes that are actually, one of them stable, the rest aren't stable, and there's not really anything to predict what type of decay they're going to take. Some of these take years. Look at that, 1.6 times 10 to the 6th years. 1,000,000 years. Yet, we go to beryllium-8, and it's got a half-life 6.7 times 10 to the negative 17th seconds. It's gone. I mean, it was gone before I said gone. So half-lives are all over the place, yet the curve would still look the same thing, and it'd still do the same thing. Alright, so we could actually apply that in something like this. So if we had a sample of strontium-90, has an activity of 1.2 times 10 to the 12th decays per second, so relatively reasonably high activity. What's the activity going to be after 59 years if it has a half-life of 29 years? We're going to do the fraction as well, but to get the actual activity, we're using an equation we just had. So the natural log of A at any time equals the negative of natural log of 2 over K, over T1 half, times the time plus the natural log of A hot, or the original decay time. So we're going to solve for the new decay. That's this. Now we do have the half-life. It is 29 years. And we do know how long we're going to let it wait, 59 years. And we know the original decay of 1.2 times 10 to the 12th. Alright, I need to bring out my calculator, and I'm pretty sure I wrote over where, yeah, I did. That's okay. I can move this over here. So I'm going to solve everything here on the left. So I'm going to start with my natural log of the 1.2 times 10 to the 12th. Natural log of 1.2 times 10 to the 12th. Close those parentheses. And then I'm just going to subtract this stuff. Minus the natural log of 2 divided by 29 times 59. Gives me this, which isn't a useful number. I need to do the inverse natural log of this. So inverse natural log, I get a decay of 2. Let me see if I got two scientific figures on. Yeah, so 2.9 times 10 to the 11th. Alright, it also asks what fraction is remaining. When we're doing that, it's probably easier just to see based on the number of half-lives. So if we're at time 0, one half-life was at 29 years, and that would be 1/2 of it. It would be 2 half-lives, 58 years, would break that down to 1/4. Well, we're a little bit beyond that, so we're approximately 1/4 of its decayed, or a quarter of it. And technically, if we actually use that same type of logic, I could have actually started with that 1.2 times 10 to the 12th and just multiplied by the 1/4. And you notice how we get almost the exact answer? And that's really because it's going to be close. We are dealing with the fractions, but the fractions are based on the half-lives. Alright, where this gets used a lot, what I mean by that, the half-life is dating of things. Now, carbon dating used a lot on anything that we suspect is man-made, mainly because it has a short enough half-life that it can actually study things, 10, 20,000 years ago without too much difficulty. Anything older than that, like if we wanted to check the old age of a rock, carbon's probably not the best way to do it because the half-life is too short. We need longer dates for that. But if I wanted to test something from ancient Egypt, it might be a good way of testing it. So that's what we're looking at. We're looking at a sample of wood from a mummy case, and we want to know how old it is. Alright, so it has a specific activity of 9.4 decays per minute per gram. and we want to know how old the case is if we know that standard carbon-14 has a half-life of 15.3. So we're using that exact same equation. And now we're just going to plug some things in. So our A that we're looking at is that 9.41. I'm going to leave the units off. I just need to make sure they were the same, and they are. So we're going to be able to use those interchangeably. Natural log of 2 over 5,730. We're going to solve for that T. And this is 15.3. Now, a decent idea, or a rough estimate, we are seeing that this is not quite half of this. So we haven't kind of really decayed it that much, but it's going to be close enough that we can use that to give us in the ballpark. But to solve it all the way out, we're just going to do the natural log of 9.41, and I'm going to subtract this minus the natural log of 15.3, and I do get a negative number, but that's going to take care of it. So I'm going to take this number now, multiply it by 5,730, and divide it by the natural log of 2, and I get a T of 4,020 years. I only got 3 significant figures. Ooh. 4,020 years. Did that again. I think it'd be pretty neat to see that, and also get to do the test on that. But 4,000 years old, and if we get those measurements well enough, we can say that's within a decade of that age. All right, transmutation. Oh, I like that. That should not even be there. Transmutation is the art or the science of turning one element into another element. Now, the earliest known scientifically studied transmutation was done back in 1919 with a guy named Ernest Rutherford. He took some nitrogen and bombarded it with some of those alpha particles, and what came out was oxygen-17, and it ejected a proton as well when it happened. Now, he actually made this little notation, what we see right here. And all that says is the reactant nucleus, the particle in, the particle out, and the the product nucleus. So we do have a balanced equation that would look something like, let's see, 1, 1 for a proton, and then 14 plus 4 is 18. 18. 7 plus 2 is 9. That's how that comes about. Oxygen 17. Now, it turns out this doesn't happen in nature too easily, because we need to actually get that to collide with the nucleus. To get that to happen, we need to speed up that particle. Now, early days, linear accelerator was a great way of doing that, and it really is very long tube. That's what they're showing here. This is the one that's in Stanford University. It might still be there. I doubt it's in use, but they're just going to run a bunch of charged plates, shoot things across, hit a target, and that causes the transmutation. Now, modern day, to take up less space, they basically just put that into a loop, and we have the cyclotron accelerator. And if you can imagine, just actually get it to one radius and let it go over itself all by itself, you can go with even larger. The Large Hadron Collider, it's in Europe, 27 kilometer circumference. I don't even know if that's what it looks like in there, but I think that'd be a fun place to get to go hang out and walk along or run along there. There's a that'd be a pretty well, it's not quite a marathon. It's not a marathon, but it'd be kind of fun to run it. But they're getting a lot of things there. They've added a lot more significant figures onto our masses of our protons and neutrons and such, and figured out what quarks and such are and the like. Well outside the range of chemical or nuclear chemistry. All right, various different ones that we do, and these are all the ones that are down at the bottom of the periodic table that we use to prove we could make cool things. So got americium, curium, berkelium, californium. Nowadays, most of the time when we do transmutation, it's to make radioactive isotopes for medical research or scientific research. We often make oxygen-18 because it's relatively stable yet not found in nature, but we can use it to actually tag certain things in chemical processes. And then in the nuclear world for medicine, we do it so we can actually check on people's health and such with CAT scans, with the radioactive dyes and such. All right, that brings us to the fear of nuclear chemistry, and that is the radiation itself and the dangers of it. This gets actually this is where the scary part of the radiation comes in, because most of us are somewhat safely and rightfully scared of what a nuclear radiation can do. But it turns out we can kind of protect ourselves in many ways just based on what type of material it is. Because it turns out those decays per second and that half-life, it really matters what other things are going on. So what type of radiation. Because if it is something like those alpha particles, they don't penetrate very far. And they actually can be stopped with simple things like clothes most of the time. As long as they're not super accelerated, so if they're coming off a natural source, they're not going to be able to do a lot of damage. Now, if you're in a room full of something giving off a huge amount of alpha particles, it might eventually do some, but a standard alpha particle, you can protect yourself. Now, the beta and gamma, a lot more of a problem, because those actually go right through your clothes. Heck, to a degree, approximately 10 centimeters. So that's like saying the average gamma particle can go right through you in places like your fingers and your wrists. It didn't even really slow down, it just kept right on going, which might be good. But the problem we have to worry about gamma is if it does collide with something, it's got enough energy, it can knock electrons off atoms that are supposed to have the electrons and make ions where you don't want them to be. Alright, so that's why they started actually, rather than just using those decays per second, they started using RIMS and this RBE, because those actually relate to the amount of tissue damage it'll do to humans or mammals. So those RIMS are a lot more beneficial to us on knowing how bad things are. Alright, so what I mean by RADs and RIMS, well, it turns out we do get millirims from natural sources. Matter of fact, if you live in a concrete house, you can potentially be getting twice as much radiation a year than if you lived in a brick house or a wood house. And that's really because the density, it might be in there naturally, it can't escape too well, various different reasons why it's higher. And if you go get x-rays, like if you go to get a lung x-ray once a week, might be a bad thing to do because a lot more rads in there. So that's why they're a little bit more dangerous. But to put all these in perspective, these are numbers. But the biggest reason you don't have to worry about them too much is the amount it takes is pretty darn high. So 5 RIMS might cause some issues. And if you go back to these numbers, look how long it'd take you to get up to 5. You have to live in, what is that, about 10 different houses simultaneously? Or no, 100 different houses almost simultaneously. But we have to go up pretty high before we have major issues. So the 50 plus and the 100 plus, those would be bad, but we're not, none of us are typically seeing anywhere even close to that 5. You have to be doing something interesting job to be anything higher than that. Alright, various different ones we do use in the medical field. So these are getting less used, but they still get used on certain cancer treatments and such. The most common of these actually is technetium-99, and it actually is a gamma emitter, but it's actually very good at actually a small amount will do a very good job of contrasting anything that's not really supposed to be there. So almost anything cancerous, technetium can help you identify it. It is getting to be a little bit more of the last ditch type thing. There's better things to use, but it still is the most commonly used ones. Now we have two different ones here for iodine. That really is, one of them's more for detection, the other one's more for treatment. The one that's for treatment just has a longer half-life, so it stays more radioactive longer, and that helps destroy cancer on the thyroid. Alright, the reaction pathways are kind of interesting. Alright, up on the top here, got this interesting reaction. This, with this little functional group here, that's a carboxylic acid, and this is an alcohol. Well, it turns out all carboxylic acids and alcohols will react, as long as there's a little bit of acid here, and make this thing, which is an ester. Alright, that's all well and good, but early scientists, when they're looking at this, they have a simple question. Alright, does this OH come off with that H to make this water, and then this O connects there? Or, let me erase all that I just wrote. Or, is it this OH takes that H, and then this O attacks? Both of them are possibilities. Maybe both happen. But there is an advantage to knowing which way it goes. So what we could do, now that we understand how radiation works, we could make a bunch of O18. And it turns out if we make a bunch of O18 and actually attach it to the alcohol, we see that that O stays on the carboxylic acid, but it stays as the ester. Yet if I put it over here, it sometimes ends up as part of the water, and it sometimes ends up here. Matter of fact, it'll sometimes end up here. So it kind of ends up everywhere. But if it's here, it's only ever there. And what that told those early scientists is, this is what happened, and this OH and that H left together. So we can use it to help understand those pathways, help us understand biological pathways as well, because it turns out even though O18 is not natural, has too many neutrons, it's actually stable. So it's not radioactive. So you could actually drink water with some O18 and it would taste just like water and behave just like water. Alright, where we're using it a lot more nowadays is PET scans are getting a little bit more common. PET stands for positron emission, so we're putting stuff into you that actually is giving off positrons. And I like my Norma L and Alzheimer's S. Yeah, got to fix my font there, but that's kind of cute. Alright, don't see this too much anymore, but we used to actually treat some of our produce seeds with radiation. And it turns out the irradiated seeds did not actually develop little funguses easily. This is not, we didn't treat this with radiation to create this. The seeds themselves were treated. Don't see it as often anymore. We have better ways to do it that don't have the fear factor of radiation. Alright, last little thing we look at in this that involves math is this fact that certain atoms are held together better than others, even certain molecules. We call that a binding energy and such. And what I mean by that energy difference, turns out if we back up and think about our formation reactions, this is a formation reaction for water. Water is made up of hydrogens and oxygens. But if I were to actually get that delta H of 934, where that mass is, where that energy is coming from, is the mass changes. So like if I were to very accurately weigh here and very accurately weigh this, I would see that those two masses do not add up to give me the same mass as the water. These add up slightly different, and that difference produced this energy. And it really is that E equals mc squared. That actually applied to the mass of the chemical reaction. Now, it is a small mass difference. If I go to the scales in our chemistry lab and try to do this, I'm not going to be able to detect that. It's a very, very small mass. So when we actually said back in Chem 1 that mass is conserved in chemical reactions, it's not quite true. We have to go pretty far out in decimals to see it, but there is a change. Now, we are going to see it on individual atoms. So what we're going to do is look at figuring out the binding energy of an iron nucleus. Now, what we find is something kind of interesting. So I had to dig, and I got this from the internet rather than your textbook because I was able to get far more accurate number. That's the actual mass of an iron 56 atom, an AMUs. And then I got the mass of protons and a neutron down there. Alright, so I know that an iron 56 is made up of 56 protons, not 56, made up of 26. I get that from that periodic table, right? And therefore it's 30 neutrons. So my mass difference, or the delta M, that Fe goes through when you build it, is based on 26 times that mass of protons and 30 times that mass of neutrons, and then subtracted by that 55.9349375. Alright, we're going to bring up the calculator and actually solve that and see how small this mass difference is. But there is a mass difference. So, alright, 26 times 1.0076276466621 plus 30 times 1.00866491588. Close parentheses. Gives me this big number. Subtract that from 55.9349375. Gives me 0.514198. 198. Obviously I have more digits, but I'm actually going to just use those. Alright, that's the mass difference. Now Einstein said we could do this equals mc squared, and this m, even though it's a delta m, is the mass we're going to use. So the E equals that mass times the speed of light squared. Now, I do want my energy, I'm going to get it in joules, so I need to convert these AMUs into kilograms. Well, that's perfectly fine because I do know that 1 AMU happens to weigh 1.6605 times 10 to the negative 27th kilograms. And then I'll multiply it by the speed of light squared, so 2.998 times 10 to the 8th meters per second squared. Let's see what we get if we do all that. So, multiply that 5.1 times 1.6605 times 10 to the negative 27th times 2.998 times 10 to the 8th squared. Not a lot of energy. 7.674 times 10 to the negative 11th joules. Alright, now that's the binding energy of the entire nucleus. To get the actual binding energy, and we typically weigh it and measure it in something called mega electron volts. To convert a joule into an electron volt, 1 mega electron volt is 1.602 times 10 to the negative 13th joules. And then, since this is iron 56, we're going to divide that entire thing by 56. So, divide this by 1.602 times. Ooh, I lost my 2. 2 times 10 to the negative 13th. Going to be this big number, and divide that by 56, and we get a binding energy of 8.55. Now, that's not all that bad, but it wants us to compare that to carbons, and you can look that up in your book, or you could solve it from this. That's why I gave us the atomic number here. The mass of a carbon-12 atom is 12. It's defined that way. Everything was based on it. So it makes that just 12, but you'd actually put in 6 and 6 here and do the same type of thing. But if we actually bother to calculate it, we see that the binding energy per nucleoid is about 7.4. So this is less stable than a carbon by considerable margin. But we would predict that we are getting heavier. All right. When we start talking about the predictability or that stability, we actually see that the binding energy of an iron is about its highest. After that, it stops dropping down, and it's lower than that when we're smaller. But we see that that difference actually leads us towards the prediction of whether or not it's going to be favorable for fusion or fission. Now, fusion is where we cram two less stable nuclei or smaller nuclei together and make a new one. And that's what they're working on in the theoretical physicists right now. And everybody and their brother says we're, decades away. But up until now, only thing we can do in America and the world is fission. And fission is controlled for nuclear power. But we take larger nuclei and let them fall apart into smaller ones, and that's what the fission's about. All right. And that's what we're looking at the next thing. So nuclear fission, one of the easiest ones that we actually have studied well, or we've studied a lot of, is uranium. Matter of fact, the first two nuclear bombs dropped on Japan, Fat Man and Little Boy. Little Boy was a big, huge chunk of uranium that was split into two pieces, and all that the bomb did was shove the big piece into the small piece. Once we had a big enough mass of uranium-235, it did this all by itself. So this whole neutron wasn't necessary. The mass of the uranium-235 was enough that a neutron was being produced spontaneously or by itself, and it was just enough neutrons that it went through fission all by itself. Released a heck of a lot of energy, cascade effect, etc., because this happens and it creates a bunch of more neutrons, and those hit more uranium-235s, on and on and on, until there's no more uranium-235. And this all happens ridiculously fast, and we get a big, huge 20 kiloton bomb, or whatever it was for the Little Boy. To control this, though, what we actually do in nuclear power reactors is use control rods. And they really do what they sound like. They control the reaction. It's the same nuclear reaction, but the control rods will slow those neutrons, and that's what they're designed to do. They stay down in there. The neutrons can't go as fast and combine with the fuel, so the explosion that takes milliseconds outside of the environment takes a year or so. And the entire time it's reacting, it creates a huge amount of heat. We let that heat, we transfer that into a container, heats up water, which turns a steam generator, and we make nuclear power, or we make electricity off that. Fusion's what they're working on. The go-to design right now is this little Tokamak design. So the concept is we're using superconductive magnets to keep the plasma, or the nuclear reaction, in a very contained small area, and that's really because this is going to be millions upon millions of degrees, and if it were to contact anything metal, it's just going to instantly melt it. So smaller amount of plasma, very well contained inside this environment, and theoretically we're close, but if we figure that out, the waste amount will be less, and this will be a safer power, and technically green, because we're going to be making a bunch of helium when it comes out, and the helium will be non-radioactive. All right, that finished this chapter up. Have fun with the worksheets.